Good afternoon. Welcome. This talk is the story of the incredible heavy lift that it took to put standard atomic into CUDA. It didn't take a decade because we stopped to smell the roses. It took a decade because there was an incredibly long, dependent chain of things that had to go just right in order for it to happen. My name's Olivier Giroux. I'm a GPU architect, have been for quite some time, and I'm also your chair of concurrency and parallelism. And in this talk, I have the opportunity to really join together my two jobs. I get to talk the whole time about both at the same time, instead of having a portion of my talk that's about GPUs and a portion of my talk that's about concurrency and parallelism in C++. The whole talk is only about this. All right, so I'm a member of a couple of communities. First and foremost, I'm an NVIDIA engineer. I've been an engineer at NVIDIA for 17 years. I've been in the architecture team the entire time. I've been working on the SM for the last 10 years. So that means, Kepler, Maxwell, Pascal, Volta, Turing, next, and so on. I've been a C++ user since 1997 or so. I'm a member of WG21. I'm the chair of concurrency and parallelism. And I'm also a member of this memory model community, which is a relatively small group of less than 100 experts who go around and fix up memory models all over the place. All right, so here's the context of our story. Our story, 1993, NVIDIA is. 2007, NVIDIA ships CUDA C++. CUDA from the first is a C++ product. CUDA C++ is a C++ product, much in the same way that Visual C++ is a C++ product. It's got a bunch of extensions, but its base lingua franca is the C++ that we know and love. All right, 2011, C++ gains stood atomic. CUDA C++ does not gain stood atomic at the same time. Stood atomic arrives in CUDA in the 2019-2020 timeframe. And this span of time is the subject of this talk. All right. Let's start in 2011. And sort of my tiny little bit of advice to plug here is, when I think about 2011, I think the thing that mattered was having side projects. I had all my main things, and then people also had side projects. All right, so the story starts very small. Different side projects that a number of people participated. Well, one side project is some clarifications on the memory model. Our memory model was a bit too concise, and it was a bit vague at that time. And so, we start circulating, what if, we clarified this atomicity thing? What if we clarified what it means to synchronize using fences and whatnot? Okay, so we do some of that. And what's there to clarify? So on the left is an excerpt from the Spark v9 manual. And to first order, their entire memory model is in that excerpt. The Fermi programming guide, which this is not the program. This quote there is not what we put on the web. This is what we have. This is how much we have. All right. It says the rules for Fermi are based on Sun RMO, as specified in Appendix D of the Spark Architecture Manual. Okay. Based. You mean there's differences? Okay, but they differ how? And there are things in that text that are kind of implied. Okay, so we're not going to go into great detail, but I'll just give you a quick overview of how to read this. Okay, so this reads an operation X that's in dependency order before an operation Y, and X is a load, means that X is performed in memory before Y. This little bit of algebra means this when you unpack it. Well, one of the things that I wonder when I look at something like this, I wonder this a lot more now than I did in 2011. But something that I wonder when I see something like this is this thing at the bottom there. Do you mean M? What, M is a partial order or a total order? We didn't even know to ask this question at the time. And our programming model didn't say anything about that. Okay, so we had a lot to clarify. Some other side projects. At around that time, we had some forward progress stuff running on gate simulation. It would take a long time before something like that would ever ship. But it was a side project. Another side project was attending the C++ committee meetings. That's when NVIDIA joined the C++ committee. All right, well, all of these side projects, they're encouraged. And I want to say that they're encouraged from all the way up. But if people were skeptical that work on formal things would fix problems. You know, NVIDIA is a hardware company. There's very pragmatic people there. And so, you know, things that are about the workings of the machinery are obviously valuable to work on. And then things that are more theoretical, more academic, are not immediately seen as valuable. 2012. 2012 is the year that we learned that formalism can fix some problems. Here's a very simple, very simplified story. You're all going to wish that I told you a lot more about it. I'm not going to tell you more about it. All right, here's a simplified story. One day, we have memory ordering issues that are appalling. It's a legendary bonfire, and it's an epic firefighting effort within the company. There are people that worked on this, and they're still known within the company for having worked on this. And all's well that ends well. All right. So now, huzzah, the side project seems like it's part of a solution. We need to understand, we need to be on top of this memory ordering thing. So we started with this, and we had a sustained series of negotiations, drafting sessions, reviews, and sign-offs, and we ended with something like this. We had a little bit more to say, it turns out. Our memory model is quite a bit more complex. You know, Sun RMO was designed for cache-coherent CPUs, and we don't have coherent L1 caches. So there's quite a lot we need to say about what are all the steps you need to take to make memory operations visible from one thread to another thread. And we've got some other complications, like we have the notion of scopes. Our fences don't reach infinitely far. We have different fences if you're going to communicate to a thread nearby to you or a thread far from you. Okay, so that all has to go into the model. Now I'm going to give you a tour. This is the model. These are literally screen caps of the actual model, okay? So this part describes something that's like happens before. And if you're familiar with C++, you know, using atomics in C++, you would read this part and you would say, oh, that wasn't so bad. That part here, though, is a little bit embarrassing. Once you had established the equivalent of happens before, you still didn't necessarily see the data. You might still get inconsistent data. So there was this second set of rules that you had to reason about entirely in parallel with the main set of rules. And if both rules agreed, then you would have communicated. That's you know, I think it's a little bit hostile for users. So we're not all fans of this part. And then this entire part in the back there is really just documenting exceptions to the rules. They're not telling you how the exceptions work. It is merely an enumeration of all the exceptions. Okay, so that was the memory model at that time. I want to talk about a thing that we got, I think, particularly wrong. And it has to do with these three concepts: transitivity, cumulativity, and composability. All right, so transitivity is what you would remember from school. You know, a rule that keeps following along multiple concatenated relations, right? Cumulativity is a term that the memory model people created to talk about fences having a cumulative effect, where if I fence my memory, then I synchronize with someone else, and that someone else does a fence. Their fence orders memory operations cumulatively with the first fence. Okay, so the fences sort of add up. And composability is exactly what you would think. That is, if you write a piece of code with two functions, and each function is correct, and then you use both functions in your program should be correct, ideally. All right. So here is something we call a litmus test. We're going to talk about this more in a few minutes, but this litmus test is exactly what I described. We have an initial thread. It writes to X, then it writes to Y, where Y would be a flag in this case. A second thread observes this first flag and then writes to a second flag. Then a third thread sees the second flag and attempts to read the initial piece of data. Obviously, not all computers order this memory with no fences in it. Our computer does not order this with no fences in it. But suppose you put the right fences, or the fences that are intuitive in it. The question is it in fact true that the second thread will see the intended memory? Okay, so this whole part on the left could be some library function foo that pops a thing off of a queue. And there's a thread that thread 0 pushed into a queue, thread 1 popped it from the queue. This could be another library function where I say, I know that a certain piece of data has been made visible, I know the piece of data has been computed, so go ahead and do some processing on that. But unknown to the caller of bar, the way that bar does its processing is it asks another thread to do it. Okay. And in between these things is white space. Okay. We got on the wrong side of this argument at the time. What I wrote on the right was what we had in our rules, which I think is wrong. We said, if all of the fences everywhere are all of the same scopes, then yes, this is insured. If the scopes are mixed, then it really depends, and it might not. Therefore, the machine might be really counterintuitive. Okay. Well, luckily, the software team argued us to sanity, and we ensured composability. We did not finish the year 2012 with the user hostile rule. We actually said, yes, it's always insured. Okay. 2013. At the time, we still had yet to see other memory models, so other GPU memory models. So we knew of ours, and we knew of the warts in ours. I just aired a few of them. We knew of the warts in them, and so we felt like, even though we had just done the whole drafting and sign-off and negotiation and everything, we felt like doing it again. So then we're going to write an entirely new model. Here's how it starts. So we know we have certain elements that we have in our architecture. We've got thread groups. We've got scope fences. We have this concept of a generic address space, which is very NVIDIA as far as GPUs are concerned. And what I mean by that is, yes, we have scratch pads. Yes, we have global memory. Yes, we have thread stack memory. But when you form a pointer on an NVIDIA device, your pointer does not carry type information as to which of these things it is. The machine automatically goes to the right place every time. Okay. And we have barrier synchronization. So these are the elements that are unique to us that we knew we needed to bring into this new model. But by now, we're a little bit more familiar with other models. We've just been through this other exercise. We learned a bunch. We've been at the C++ committee for a little while. We've learned a bunch. So there are things that we see in the C++ and Java memory models that we like. And I'm going to explain the American note in a minute. C++ and Java make a distinction between atomic operations and non-atomic operations. Did you notice that CPU memory models don't tend to make that distinction? CPU memory models promise that if you touch memory, you always touch it atomically. That's kind of over-promising, I think. If C++ is going to make this distinction, it's a really useful distinction for me to know about as an implementer, a machine implementer. So we decide, yes, we're going to have this distinction between atomic loads and stores and non-atomic loads and stores. We really want the one happens before. We don't want the two relations that you need to reason about. We want it to be always transitive. And in C++, there are actually 3 memory model subsets. If you look at it, you could take the C++ memory model and bin everything into 3 bins. There's a relaxed consistent subset. There's a release consistent subset, the release and acquire part. And there's a sequentially consistent part. And they interoperate in a way that makes sense, but you can see the elements of these 3 subsets, and we like that too. We wanted that in our model. But we were also looking at hardware memory models, which are also interesting. So the power and ARM models tell you memory is not a total order, meaning you might have an assumption that if you do a bunch of loads and stores, no fences, you just throw loads and stores into the machine, that the machine picks a total order for all these operations. And it's true on x86. But Power says no. Every core can observe a different order that memory operations settled into in the absence of synchronization. And it turns out that that's really empowering for us. So we borrow that. Dependency order is well specified in CPU memory models. It's very poorly specified in C++. But it's well specified in CPU memory models. There's a hard out of thin air guarantee, which unfortunately I cannot get into. Yes. And there's something else that's neat. The CPU memory models, the hardware memory models, don't have undefined behavior in the presence of races. They have extremely loose behavior, but not UB. At the end of the day, we're going to say your completely racy reads and writes will obtain a byte that you wrote and not the credit card number in the other process over there. Right? Okay. Yeah, because you couldn't sell hardware if hardware said that. Right? All right, okay. Now, one thing that I think is really interesting to note is that academics sort of neatly sorted themselves into 2 buckets where most of the American academics are looking at things on the right and most of the European academics are looking at things on the left. So sometimes you'll be in a little group of memory model experts, and you'll notice, why is no one bringing up the partial ordering issues? And then you realize, oh, it's because I only have people from UI, UC, and MIT with me right now. Okay. So now that we had loftier goals, you might imagine that took a little bit longer to explain. And I'll give you that quick tour again. So actually the front part of it is a prose version of the memory model, which is full of examples. And that's actually kind of nice. The semi-formal part is the rest, which if you look at the semi-formal part, it's sort of the same size as the previous one. So we did a pretty good job there. And that thing at the end is advice to the reader. The last page is exceptions. All right, so that's a lot better. All right, so what were others doing contemporaneously in 2013? What were they doing with their memory models? All right, so did I say GPU elements there? Because it's not going to be about us. All right, so, well, the first thing is they're not really looking at the CPU-style memory model specifications. So they have undefined behavior for races. Their out-of-thin-air guarantee is pretty thin. It's the same one as in C++. The dependency order definition is also pretty thin. It's the same as in C++. And they don't speak too much about the partial ordering, but it turns out they sort of walk away from it because their release-consistent operations are going to be sequentially consistent. All right. They have multiple address spaces. They don't have a generic pointer facility where you can form a pointer into a piece of code. It doesn't matter whether it's in Scratchpad or global memory. Every function needs to say that this is in Scratchpad or this is in global memory. They end up with 2 happens befores because they have 1 in Scratchpad and 1 in global memory. They're sometimes transitive for the same reasons as the mistake we made the year before. And they have something that's really popular among the American academic crowd, which is they don't really have RC and SC. They have RCSC, meaning their load acquire is a sequentially consistent load. And their store release is a sequentially consistent store. They're sort of lacking that weaker definition, which really enables the partial ordering to be exploited. Okay, so that's what existed at the time. So we made a pretty fancy model. Okay, and I think gentler in many ways, but not always. I mean, it's not gentler in all ways. It's because I will admit that RCSC, without the slash, is gentler. It's just, I don't think it's good for implementations. Okay, could we have shipped it? Well, no, we can't ship it. We can't ship it in 2013 because we don't have the hardware that that model really wants. We're working on it, but we don't have it. Also, it's kind of written like it's 1990. I mean, remember that we started from this Spark 9 manual. Then we took their like 3-line little example and we turned it into a 20-page monstrosity. Okay? That wording technology was never intended to be stretched this far, and we can't prove any formal facts about it. Okay, so what's going to happen now is we're going to catch up 25 years of science in about 5. All right. 2014. This is when we really became comfortable with partial order models, and this is when you will now become comfortable with partial order models. All right. The first thing that we need to have in our vocabulary is we need to understand what is the meaning of atomicity. And here's a citation. This is a book. We're going to have 2 definitions of atomicity. The first one, called single copy atomicity, means that when I perform a memory operation, I never have an interleaving of that operation with another one in the middle. I perform a load entirely or not at all. Same for a store, same for an atomic grid modifier. Multiple copy atomicity is something else. It's saying that not only are the operations not, you cannot observe an interleaving internal to the operations, but also they are part of a single total order across the whole machine. Okay? So the analogy is the teeth on a zipper are indivisible, and then what you get at the bottom is a serialization. Okay? You started with 2 streams of teeth, and you interleave them in some way, but they're interleaved in the serialization. You never have 2 zipper teeth that like happen to inhabit the same volume and space. Yeah. Okay, there was a thought which I'm going to immediately tell you that I disagree with. That the way you should define a memory model is you should first immediately say only multi-copy atomicity is acceptable. I don't agree with that, but anyway, suppose you say that. And then you explain all of the machine's behavior in terms of reordering. And if at any time you have had a conversation with someone that was debating memory models in terms of reordering, then I can tell you, that conversation you had was with that frame of mind, which I think is wrong. Okay. So you start with the same thing as earlier. You get both the indivisible and the serializable. And then you explain the zipper machinery thingy as some table of reorderings. So for example, you might say that subsequent load can pass an earlier store. And that would essentially be x86 TSO. Okay, it is enough for TSO. It's definitely true. Okay, but what we're looking for is the next step. The next step is asserting less. We're going to say, okay, instead of assuming multi-copy atomicity, we're going to only assume single copy atomicity. Now I have a couple of blanks there. So what can we say about what the result of the machine execution will be, and how can we describe the machine? Well, what we do is we treat the machine as essentially being inscrutable. And we give you some axioms about that final interleaving. We're going to say, in that final interleaving, you may find anything, but not certain kinds of inconsistencies. Certain kind of inconsistencies will not be in the interleaving. Okay, all right. Now, you're going to forget the zipper analogy because we're not going to use it again. There is no such thing as a unique total order of memory operations. Done. Okay, so how do you make a memory model? First, you consider intended constraints for some test program. So you write a really, really short little program. Like the one I had earlier. In fact, the one I had earlier is by far not one of the shortest. It had 6 instructions in it. That's huge. Usually you're going to start with like 2 instruction programs and 3 instruction programs. Okay. And you're going to think about what are the inconsistencies you don't want to see for that instruction, for that little program. So you're going to formulate those axioms over some set of relations, which you know is coming in the next slides. Then we're going to use some kind of a tool to enumerate the programs that still remain after we have constrained the executions. You're going to get that as an output. You're going to look at it, and you're going to use your intuition and your knowledge of C++ and what your intent is as a designer, and you're going to repeat. You're going to go back to the top, consider the constraints, constrain, produce programs, look at them again, and you'll just keep doing this until you don't see anything weird anymore. Okay, well, your workhorse litmus test is always MP, which stands for message passing. Most conversations about communication through memory involve describing MP. Because MP is this example of I set some data, then I set some flag, someone loads the flag, then loads the data, and the question is, at the end of all of this, does seeing a 1 in flag imply seeing a 1 in data? And you expect yes, but the reality is it depends. Now, MP is actually a stand-in for most forms of synchronization, which is why it comes up so often when you are teaching a memory model to someone. Because I could replace my flag, let's say, with mutex operations. Thread 0 begins as the first owner of the mutex, writes some data, unlocks the mutex. Thread 1 locks the mutex, and then wants to look at the data. If thread 1 is the second owner, does it mean it sees 1? The previous form and this form are equivalent. Except that in this case here, reality has to be yes. Okay, so there's going to be something about that unlock function and that lock function. They're going to need to contain something so that the it depends becomes yes. Okay, so we're going to say that we're looking for consistent results consistent with an intuitive read of the program. And that implies that there's some sort of sort key. There's sort of a notion of this happened before that, happened before this. We've already spilled the bean. Happens before isn't C++. Okay, so we want the initial write of 0 to data to be before the execution of the program. So that initialization at t0, at time 0, happens before thread 0 run. Okay, so that's before that. The store of data is before the store of flag in a way. The store of 1 to flag is before reading 1. How could I have read 1 if it was not stored before? That would not be intuitive. And then the second load is before also. And so the thing we are trying to forbid is that load being before the store of data, and hence that would form a cycle. Okay, so the question becomes, what kind of code do I expect at the comment A and or the comment B so that it will forbid the loop? And so then you expect that it's forbidden, and the reality is it's going to be forbidden, but programmer shall ensure that he's got the right code at A and B. And the author of the mutex is the one responsible for that. Okay? And the memory model tells the author of the mutex what to put at the morally equivalent A and B. Okay, I use this word before, but things in program order are notionally differently before than a read that reads from a write. Okay, so we're going to be a little bit more specific. We're going to go back to Jad's work, and we're going to actually create a bunch of different kinds of before, and we're going to use them to describe the execution. Okay, so what the program wrote down is program order. I had a series of statements in each thread. The statements in a thread are related and happens in program order. The instructions in different threads are not related in program order. Okay? What the machine actually did, the other before arrows, is what the machine did. Those are several relations. We're going to call RF, read from, the write that produces a value preceding a read that reads that value, specifically that value, not an equivalent value, this one. like if a write stores 42 and there's another write in the program that stores 42, the memory model will actually distinguish between which of the two writes you read from. Okay? Coherence order is the order in which two writes that overwrite one another are related. That's also a before, a kind of before. The next one is a little bit kind of weird, and so I need a diagram for that. From read is going to be the opposite of read from. If I read from a value and that value is later overwritten, then my read that read the value but not one of the values that overwrote it is some kind of before the writes that overwrote the value. Okay, and so you see this diagram over there. I have a W0, and it is connected to a read that reads its value. And then I have a W1 and a W2, and those are related in co because they overwrite. W1 overwrites W0, and W2 overwrites W1. Well, FR is going to connect the read to all the co-subsequent writes. Okay, it doesn't seem all that useful now. It'll be very useful in a few minutes. Okay, and then we're just going to have one more. We're going to have in Jad's work, these are the orders. Unfortunately, the specification of power is very ugly with only these four. SC is going to be a special relation we're not really going to talk about today, but it relates the heaviest fences that your machine has in a unique total order. And that is the only thing related in a unique total order. Okay. All right. Now that I've shown you these relations, I can show you a sample of different litmus tests and the kinds of cycles you are looking to forbid as you are designing your memory model. Okay, so it starts from very simple ones, like this one. It would not be acceptable to me if two writes that are in the same thread in program order overwrote each other via time travel. It would not be acceptable to me if a read could read from the future. Things like that. So you start with simple facts. Eventually you get a little bit more complicated, and then you find MP somewhere in there. And MP makes use of that FR edge, that yellow FR edge, where it says that means if this read reads from the initial value, 0, then it's connected from the initial value to it by an RF. The initial value is connected to this other stores in the program via co, which means that read would, if the cycle occurs and that read is connected to this write by FR. Okay, we're going to do this again, more slowly. Okay, but now we have the tools. It's easy to specify sequential consistency in this framework. Sequential consistency is saying that if I take all the PO edges, union all the co edges, union all the RF edges, union all the FR edges, then this entire set of edges, all union together, there are no cycles in it. That is sequential consistency. And it's so neat, it's so compact, easy to understand. Okay, so we kept simple things simple, which is cool, but complex models will continue to be complex. But the most important thing is, in the previous framing, we didn't even have the tools to describe a complex memory model. Now we have the tools. Now we're going to fill in what is acyclic in a more complex memory model. All right, 2015. 2015 is when the team learned Alloy. And it's when you will learn Alloy. Here's sort of your ideal storyline for debugging a memory model problem at your company. Say you have solved the issue of modelizing your system as logic over some graphs, as we described before. Well, you might one day be faced with some behavior of your machine, and you'll be like, I really wonder if that behavior is something that we said is permitted. So what do? You go to your closest SAT solver to prove it's not possible. And your SAT solver goes away, fan spinning, takes some time. Hopefully you didn't ask for a problem so hard that the sun is no longer 5500 K. And then the SAT solver will come back, possibly, with, you got this completely wrong. It's entirely possible. Here's a bunch of counterexamples. Great, thanks for the counterexamples. I could really use something like that. And then you go away and you debug your problem using the counterexamples that the stat solver has given you. All right. Now, it's no joke. The time complexity of this is enormous. Here is actual times on different axioms of our memory model. Actual times for solving for graphs of a certain size. You know, a graph of size 6 is not very big, but you're still talking about an interesting fraction of an hour to solve something here. And obviously, if you want to solve for a large program, large, like, I don't know, 18 operations, like you might end up having to wait years. Okay, but don't let that discourage you, because we are going to learn about this amazing tool from MIT. What do you get when you take 1,200 papers and 13 PhD dissertations and you crystallize it into a piece of software? You get this. And we're going to use it right now, and we're going to prove some things with it right now. You know your nerd cred is in there. Okay, so Alloy is, what is it? It's a really clever graph DSL for stat solvers. You do not need to be an expert at stat to make use of Alloy, because it's actually rather friendly to get into. Why is it friendly? And you're going to see the syntax, and I think you might like it. Why is it friendly? Well, it's got these lowercase keywords and curly braces, and you don't need to parenthesize this like it's Lisp, and it has C++ comments. It's got a thing that's like classes with members, and your classes can inherit. Okay, I get that. It's got a thing like pointers and some containers of pointers. And it's also got a thing like functions, although those are pure functional. They are. And it's got a syntax. You know, when I said earlier, acyclic something or other, actually, when we're going to write these axioms, we're going to have a pattern matching syntax, which is like a regex. And it's like a regex syntax that you would recognize. Like, you already know how to write many of the statements that we're going to write here because the syntax is the same. And it's got a kind of a main function. Now, that one you really need to squint. It's got a thing that's kind of like a main function, and if you cause it to execute, you're going to get a thing that's output. Okay, so it usurps familiar idioms, so you go into it not scared. Appropriately? No, not scared. You get in not scared. Okay, so first, here's the thing that's like a class. They're called signatures, and they have different kinds of members. And on the left is how you would declare such a member in Alloy. You could say member A is a set of B. And it's really as if it was a stood set of pointers to B's. To B, not B's. Same thing for the other types. Sum is a set that's actually constrained to not be empty. One is a pointer that's not null. And lone, don't ask me why, is a pointer that could be null. Okay? So I could create one of those nodes. I'll create one of these classes. I'll say sig operation. One of its members is program order, and it points to 0 or 1 other operations. Okay? Because in a thread, the last operation does not have a program order subsequent. Right? Every other one has one, but the last one does not have one. Okay. I could inherit from operation. I could say I have reads that extend operation. And I could say that I have writes which also extend operation, and they have a member called reads from, the little red arrow from before, and it points to reads, a set of reads. A write is not necessarily ever connected to any other reads. You could have, a tree dies in the forest. You can have a write and no one reads. So it's a set and not a sum. Okay. Before we can switch to the Alloy UI, we're going to have something else to say that's going to be a little bit more interesting. Okay? 2 more things. A predicate, there's 2 kinds of functions in Alloy. There are functions that have a bunch of input and a bunch of output, and then there are functions that are specially constrained to return bool. Functions that return bool are special, and there is a special kind of statement in Alloy called a fact, which says whatever this evaluates to, it's always true. meaning if that expression has the potential to be false, then any graph in which it is false is not a valid graph and can be discarded summarily. Okay? So, we're going to write one such functions. You know, in a language like this, it would have been nice if things like irreflexive was provided, but it was not. Okay, so we're going to walk through it. So function that returns bool, that's its name. The braces is the arguments. That's the name of the argument, rel. What is it? Well, that's its type. It has an arrow in here, meaning its type is a relation. And it's going to be constrained to, it can point from anything to anything. Okay, so that's not very constrained, but you can constrain it. Okay, my predicate is true if the thing on the right is an empty set, and I'm going to form this set by taking the self relation, which is a special relation where every node only points to itself, and I am going to intersect it with the relation I got going in. Irreflexive. What's acyclicity? Well, acyclicity is the irreflexivity of the transitive closure of a relation. So I'm going to use the transitive closure operator. I take a relation, transitively close, give it to irreflexive. And then I'm going to say, you know what's a fact? Program order doesn't go in loops in these things because this is the post-execution instructions, not your original program. Okay, so if you had a loop in your program, this graph considers the actual steps taken. And the steps taken are not causally loopy. Okay? All right. And so we're going to say only graphs where this is true can be considered. Okay. Now I used a name earlier. A name in Alloy, the name right, or the name operation, is a set. But obviously you have like for all and for some. So we're going to have one more fact here before we run. This fact is going to say for all name is a member of read. So for all R that is in reads, it is true that something that can be true. Okay, so the thing that can be true is we're going to say this R composition. Now we're going to stick a relation here. We're going to say from this R some relation. That's the dot. Some relation. Reverse of read from only points to one thing. What did I just say? I said reads only read from one write. I can't have, in an atomic memory model, I can't have a read pull from two writes. I read from one specific write. Okay? And this whole thing is a thing that can be true, and we said it's a fact, so it's true. All right, so how do we run things? Well, we're going to have a run statement. We can put a constraint in there, or we can run unconstrained, and then we can give it an arity, and now we're going to run, and this is what Alloy looks like. You run it. This is the code that I wrote a few minutes ago. This is the same code from the slides. Okay? And we're going to click that execute button. When we click execute, the solver will go out, and it will find all valid solutions to this set of facts and this set of signatures. It'll say instance found. We click on that. And now we get a viewer that's built in. This is so friendly, you guys. It has its own graph visualizer that comes with it, and you don't need to learn how to like output the graphs and put them through dot or whatever, right? So we get the first thing. That looks really good. I have a write, I have two reads in program order, and one of the reads from the right. Legit. I click next, and I guess we didn't constrain empty graphs. I guess an empty graph is a valid execution? Okay. Crap, we're reading from the future here. I said earlier when we had litmus tests that I don't like reading from the future, but we just did that. Okay, we're gonna need to work on that. And then we've got an operation here that's neither a read nor a write. I didn't mean for that to be valid. Okay, so we're gonna add a couple more constraints. One of them is we're gonna say that sig is abstract. You never instantiate operation on its own. You instantiate only things that extend operation. And also, we're going to say there's always some operation. So we don't get empty graphs, and we don't graphs that contain operations that are not writes or reads. Nice. Next thing. Read from the future. You see there's a read, program order, and yet we read from the second write. That's not cool. Well, we're going to say, you know what? We said earlier what's acyclic is program order. But what we meant is what's acyclic is program order and reads from. Union together. So that's the plus. I'm going to union program order and reads from. If you remember that definition of sequential consistency from the other slide, you see we're going to kind of be building towards that. Okay? Okay, this one is program order has a join in it. Read is program order after these two writes, but the two writes are not related in program order. For our memory model, we're going to say that that's not legit, so we want to stomp on that. And we're going to say, if I take any program order edge and I sequence it with another program order edge that's reversed, I always come back where I started. Okay, so I follow one program order edge. Now here I'm going to follow a reverse program order edge, which could either be the same one I just took or this one. Well, if it's the same one I just took, then I end up in idem. I end up back where I started, which is what I want. If I take the other one, I don't end up where I started. So we're going to ban any time that you follow a program order in a reverse program order. If you don't end up in the same place, that's banned. Okay, now we have a different issue. In this issue, I have a write which is overwritten, but my read reads the old value. I don't like that, but I didn't put a notion of overwriting. Remember that CO relation from before, the blue CO? We didn't put that in the model. So now we're going to put that in. We're going to say writes actually have another member called coherence. There's 0 or 1 write that follows this write in coherence order. We're going to say I can find from any write to any other write, I can find that in the closure of coherence. So because right now I'm doing a single address memory model, I'm going to say if I start from any given write and I follow coherence forward or backwards, I can find every other write. Okay? And now we're going to increase what's acyclic. Program order reads from and coherence is acyclic. Now I can't read from writes that have been overridden. Okay. At this point, if you had pasted this code into Alloy and clicked execute and then went next, 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 and then you get graph, 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 they would all look fine. Okay, but we said for 3. What if we go for 4? Well, if we go for 4, here's the pattern that we have. We have a write. It's overwritten. The overwritten value is read by a read. Then in the same thread, I read again, but I get the old write and not the new write. That is a little bit upsetting. And this is where from reads comes in. So we're going to say, oh, actually read also has a member. Prior to this, it did not have a member. Now it does. It's from read, and it points to a set of writes. It has exactly the definition that I said earlier. From reads is equal. Literally, I am not giving Alloy a constraint on from reads. I'm telling it what from reads is. It is equal to, you chase my reads from backward, and then you chase down coherence. Okay? And now you say acyclic, program order, reads from coherence from reads. And that is sequential consistency. Okay, so now we fixed the issue. Now if you were to take this and you ran it for 4, for 5, for 6, for 7, and you lived through clicking next, because n permutation creates large sets, you would find that now we're good for any number of instructions, but we're still only catering to programs that have a single address. So now we're going to teach it. Oh, and that, by the way, that memory model is the memory model of a program comprising in only one variable, and it's a studatomic. Okay, we're going to teach it about multiple addresses. We're going to do this fast. We created a sig that's an address. We say that operations are related to an address, exactly one address. We're going to say that for every address, there's at least one write to it. This is what this constraint here says. It says there's some from this address and you chase adder backwards, it ends in a write. And you also say there's always some address. I'm not interested in programs that don't have any addresses. And we're going to say reads from and coherence are constrained to be relatable through address. Okay, so I cannot read, if I'm a read of X, I can't read from Y. In order for a read to be connected to a write, it needs to be possible to go from the read to the write by bouncing off the address relation. Okay? And then finally, when I said earlier that all writes are reachable in transitive coherence, when they're related by address, of course. I know a write to X doesn't overwrite a write to Y. Okay, well now we have sequential consistency. If you were to take all of this and paste it into Alloy, you would have a model of sequential consistency that you can throw test graphs at and ask for proofs and check if the patterns are as you understand them to be. It's a complete model of SC. Okay? All right, with a few more edits, you get ptex. You know, it's a lot of text here, but it's not that much. The NVIDIA model ends up being 180 lines. You know, think about 180 lines of C++. Like, you don't write a major application with that. But I wrote a major memory model in 180 lines. And it's still relatively easy to use. So for instance, I can ask run ptexmm is true, so that's my memory model, is true, run ptexmm, and not irreflexive this chain here. That chain is the chain that describes a relaxed MP execution. Okay? So here you can say, what's a valid relaxed execution of MP on ptex? And if you were to scrutinize it a little bit, you'll see there's some acquires in the thread that reads, but the thread that writes does not have a release or a fence. And so that's why the relaxed execution is allowed in this case. Okay? And I use the team to clean up the graph because the graph would be enormous with all the various relations. All right. 2016. In 2016, we learned that C++11 is unimplementable, which is a bit of a big deal. There's a perplexing counterexample that's found. We run something like check that ptexmm implies C++mm. So an execution that's valid in ptex is also valid in C++ for some 8 or 9. And this check failed. But when we dove into it, we discovered actually the manner in which it fails is common mode with IBM Power, which is concerning because as far as we knew, this actually was implementable. And other groups actually find the same thing elsewhere. So here's a very simple program that will not make your head hurt at all. This program is not allowed to execute without asserting. And that's because it is where the asserts are. I checked the values seen. We are not allowed to see these values. We cannot see all of these values all at once. But obviously, that makes everybody's head hurt. So what we do is we take this and we stick it in a tool called CppMem. CppMem is this website. You write in this modified C++ syntax. You put it in there and you say run. And it comes back telling you whether this execution is a valid C++ execution or not. Here, we did that, plugged it in, run, says no. The values that are in this program are not permitted to be seen, all of them, some subset of them, yes, but all of them, no, in a C++ execution. Okay, so that's interesting. But we're going to transliterate it to Power. We're going to go to this other website, which has the compiler mappings from C++ to different processors, and we're going to use the compiler mapping from C++ to Power. And we're going to transliterate it to its equivalent Power. I've highlighted this in 2 colors. The cyan part, totally meaningless. It does nothing. That code does not constrain the Power execution in any way. Only the yellow constrains the Power execution. But it's a relatively small test. Store to X, lightweight fence, store to Y, and in another thread, overwrite Y, heavy fence, read from X. You don't need to know the Power memory model to adjudicate this one because there's a perfectly valid other website which has all the litmus tests with the constraints for Power. And if we dig into this, we're going to find a litmus test called R. And R says that given the constraints that are here, the execution is allowed. Sync in that PDF stands for heavyweight sync, whereas lightweight sync is lightweight sync. So this says if you want to forbid the cycle in R, you need heavy fences on both sides. But our program did not have heavy fences on both sides. When we took the C++ and transliterated via the compiler mappings, we ended up with 1 heavy fence and 1 light fence. Therefore, this execution is allowed. Okay, so this is a tough choice. What do we do now? And there's like, what does NVIDIA do now? What does IBM do now? What does the C++ committee do now? At this point, we could either declare the compiler mappings are invalid, and then that would mean untold petabytes of compiled code must be sent to DevNull. Somehow, how would you even achieve that? Or we need to make a change to C++. We need to say, actually, C++ got this wrong. And that's what we ended up doing. Years later, we adjust the C++ memory model, and it's in this paper. Okay? And because it's retroactive, then binaries are okay. All right. 2017, a lot happens. Do remember to enjoy the good times. Don't always be miserable. I mean, we tend to be cynical and whatnot. It's finally here. The hardware we were waiting for earlier, it's here. The following is not hyperbole. We made a new kind of computer. What I mean by that is, you know, the SIMD, SIMD, MIMD, SPIMD. We refreshed SIMD on its 10th birthday. We gave it the ability to execute all concurrent algorithms, bar none, and expressed over atomics, so make use of the memory model. But at this point, we're really, 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 really busy. You have to imagine that this made a really big splash. We're really busy. We're too busy for atomic. And I come here to CppCon and I tell you guys about the Volta C++ affinity. Okay. In 2018, you know, we still haven't had atomic. You know, we were too busy for that. But the need for it hasn't gone away. So this is where bottom-up leadership actually can work. Basically, engineers looked out for each other a little bit, and we realized we actually needed this to get our jobs done. So we're back to side projects. And we pitch a standard library, a C++ standard library for CUDA to everyone who will listen to us and some people who don't want to. And DevTechs just fall in love with the idea. That's our department of people who help developers out in the field. I have some quotes. They loved it. And one of the biggest improvements, an essential step to move CUDA into the future, and the natural way to get clean, performant implementations. All right. This pushes it over the top. I come here, there's a demo. At the time of the demo, it wasn't actually committed work, which is why it's SIMD : stood and not CUDA : stood. But the demo and the dev text, we push it over the line, and now it's the committed plan. All right. In 2019, we learned how to update the atomic header, and in a very brief way, you're going to learn it now, but probably not as much as you wish. Okay. How is libcxx's atomic header structured? Okay, so at the top level, you have an atomic class and a specialization for pointer, and it inherits from an atomic base, which handles the integral specialization. That in turn contains an internal abstraction layer called underbar CXX atomic. This is an object, it's a struct. That's the internal abstraction layer which shims the publicly accessible objects from the internal built-ins. That inherits from a couple of implementations. There's a C11 implementation, there's a GCC implementation, and it is possible for you to provide your own, which we do for CUDA. And one of the changes that we upstreamed to libcxx is we added an intermediate layer which allows libcxx to handle the non-lock-free atomics without any compiler help. If the compiler doesn't support the non-lock-free atomics and it only supports the lock-free ones, then libcxx will create an object with a built-in lock using only the built-in ones. This was not supported in libcxx before, and it's a feature CUDA needed, so we wrote it and we gave it to the community who could use it in freestanding implementations in the future. Okay. The CUDA enablement part. We enabled this built-in mode, and we put it in the right namespace. We supply our shim layer. Our shim layer starts from that CXX atomic base. We have two versions, very small objects and normal objects. We don't have 1 or 2 byte atomics on GPUs, so the very small objects need to be padded up. We do that there. And then we may have some alignment issues, so we fix that with another alignment wrapper. And on the host side, we just send all this code to the host atomic implementation behind the abstraction layer. You know, and then there's a small matter of like providing 100 built-ins, which all kind of look like this. There's a bunch of inline ASM, and then people who've written some of this code in standard libraries will know you end up switching on mem order, which is really annoying. And then there's an implementation for Volta and an implementation for Pascal. There's this scope tag thingy. Okay, well, that's part of our non-standard extensions. Scopes are added. The type hierarchy is enhanced with scopes. And we pass that in through the type system so that the way you would use it in CUDA is like this. A CUDA atomic of T of scope device. Okay, now you might say, but wait, what if I want to mix scopes? That is fully supported. It's fully supported, but not in the C++ layer, because the odds of getting this wrong are very high, and we're going to help you write fewer bugs. So if you really, really, really need to mix, then you can use the inline ASM, same as you could before this change. Okay, and we have some extended atomic operations, like fetch min and fetch max, which maybe we'll bring to SG1. Okay. If you'll indulge me for like 4 more minutes, let me tell you about that 10th year. It's been 9 so far, if you were keeping track. That 10th year, it's not really me, it's you. Okay, the 10th year is now you need to adopt this. You need to move off of volatile in CUDA code and to stood atomic. So let's give you just a couple of examples. So before, you would notionally write code like this. You know, you'd use a volatile for your flag, and then you'd have a separate fence, but really it's more efficient if you can fuse the fence with the flag operation. And then we've got these atomic operations which ask you to cast thing off volatile, and you end up using an atomic instead of a store. Now it's damned if you do, damned if you don't, because if you use a store, then now it's UB in C++. You know you can't have data races on volatile in C++. Okay, so that's all rather crufty now. What can you write now? You can just use atomic and atomic operator equal, or you could use store with memory order release, or in the C++20 implementation that we'll have later, you could use that and the notify operation. Okay, on the polling side, the reverse happens, all the same, but the reverse. Now, on the polling side, there's a special gotcha that I have to tell you. A lot of people have written this code, and it's not great. Sometimes people omit the fence. They rely on dependency order, and they mark their data volatile. Okay, that is just wrong in so many more ways. And you fix all of that by switching to stood atomic. Right? So you can write it like this, or you could write it like this with memory order require. Or in C++20, coming up later on, you can use the wait functions on the GPU as well. All right. One special thing that we took care of for you is the whole host device integration. Imagine writing a host device function that needs to do some atomic update. Well, on the device side, you can use the atomic operation. But what do you write on the host side? On the host side, you're supposed to use stood atomic. That's what you're supposed to use, but you're not using it right now. So you're going to use a whole bunch of inline ASM. You know, I think it would be rough to go through code review for that. Well, what do you do now? You just use atomic because it works. Okay. All right. There'll be more things coming to libcxx in the future. I look forward to telling you more about it, but not now. In conclusion, it's kind of mind-boggling that it took 10 years to do this, but I think you could see that there was an enormous amount of work that needed to happen. It's not just the work. It's that we didn't even know what work we needed to do when we started. You know, we were interested in making clarifications, and we were well-intentioned, you know, to make a nice, clean programming model for our users, but we learned so much along the way that almost everything we ended up doing, we didn't know about at the beginning. And we could have failed every single year. Just make no mistake about this. There's nothing automatic about doing work like this. Every single year, we could have turned away from the cause. Every single year, we could have made a memory model that was incompatible or failed to do the work. But, like I said, we still need your help. We need you to move off of volatile and onto atomic going forward. And that's it for my story. Any questions?
With the normal CUDA atomic operations, there are type limits depending on the hardware architecture.
Yeah.
How is this handled?
We are not providing this far back in time. We're providing this for Volta entering primarily, and we also are going to support Pascal. Although, as you could see in the code, the Pascal implementation has sort of a different quality to it than the Volta entering one. So really, the Pascal support is provided to help you port but we are not going to support Maxwell or Kepler.
Okay, thanks.
Have your colleagues working on your IDEs that you provide considered providing automatic support for transformation from volatile to atomic?
Oh, that's a wonderful question. I don't think we have ever discussed that.
Yeah. You might know someone who can do things like that.
Yes. Well, thank you, everyone. And have a great evening.